All right. So you know that you're kind of a failure as a business owner when you get to a point where your own stuff has not worked for about almost 2 weeks and you haven't made the time to fix it because at the end of the day of doing your regular electronics repair, your brain is so fried that you can't fix your own shit. And honestly, usually I just buy new stuff. Like when it comes to my home stuff, I am not fixing my own motherboard. I'm not fixing my own television. I'm not fixing any of that. If anything stops working, it's time to buy a new one. But the reason I want to fix this is because this thing is about 11, 12 years old, and it was like the first amplifier that I ever fixed. So this thing has a lot of sentimental value to me. And it's been with me to a lot of places, which is why the fucking thing has no top case anymore. It's missing the feed. But still, like, it makes music. I use it in my office every single day with the TLCS 3.6 speakers I have here. It's a Parasound HCA 1000A. It's a really nice amplifier. And I really do want to fix this and make it work again. So I figured, I know it's going to be a really long time before I actually have the time to fix this, if ever, with the whole having 2 employees and me being the only one that does board repair crap here. But I just want to go over it in here. I thought I would provide a little bit of a video on a different type of electronics. I may eventually do a video of me actually fixing this, but if I do, it's going to be this half-assed effort that's kind of done in between all my actual paying jobs. So let's just go over to the schematic here. By the way, before I even mention anything about how this thing works, I want to say 2 things. The first is, feel free to correct me if I get any of this stuff wrong. I don't want people to think that I'm an authority on this, because a lot of people are going to think that because I'm good at troubleshooting the things that I regularly troubleshoot at my job, that automatically assumes that I'm as good at this stuff. The last time I did this professionally was over 7 years ago. I started doing the pro audio stuff professionally about pro audio and home audio and broadcast gear and like hi-fi gear. That I started that about 10 years ago. And there was no college experience there. I was pretty much clueless. And I got to a point where I was pretty good at it. It's a skill set that I haven't used for 7.5 years, right? So when you don't use a skill set for 7.5 years, you're not going to be as good at it. So I don't want people to think that I'm as good at this or, as explaining all this as I am with everything else. So if any of the engineers or the pro audio people or the people who are good at repairing old vintage audio electronics want to correct me in the comments, I encourage you to as much as you can. And the second thing I want to mention here is how I got this schematic. So, because this is something that I think is going to be lost on a lot of the newer generation. Because one of the things that made me sad with some of my other videos that I've done, it's not that the people that were arguing against me having schematics, wasn't necessarily the argument they were making. It's that some of these people, like, they were mentioning, like, I'm still in school, and I go, oh, what college? Oh, it's high school. And they were arguing, like, well, why should they have to give you the schematics for stuff? And the reason that makes me sad is because there's a whole generation of people that genuinely don't understand why it's a problem that I cannot get schematics for the products that I work on, right? So, if I want, again, I'm a licensed business at this point. So I have a license from the Department of Consumer Affairs. We have years of experience. We have years of reviews providing positive service to customers. I think I'm at a point where I should be able to buy a MacBook Pro schematic if I wanted to from the distributor, but I can't. It's impossible to do any of that. I asked for a schematic for this amplifier when I was about 16 or 17 years old. This amplifier is made by Parasound, as you can see here. And what I did to get the schematic is I emailed Parasound. I told them, I'm just a kid that wants to learn, and I have this amplifier that I was able to get a hold of, and I'd like to see if I can make it work again. I emailed them, and you know what they did? I didn't even have a receipt. I didn't even buy it. I didn't ask for money, and they just gave me the schematic. They emailed me this PDF file of the schematic, which I could then use to repair the amp. And and again, I wasn't even 18. I didn't have any way of paying for it. I wasn't a professional repair shop. It was just part of the culture. It's like, here, we released the, take it. Here. It's not like they were, and the thing is, it is, somebody could put something like this together in their house, right? If I give you this schematic, you could reasonably put together this amplifier in your home. I'm not saying it would be easy to, do your own PC board. I'm not saying it would be easy to, construct everything, but I'm not saying it's easy. But it's totally doable. Somebody could look at this schematic and just put this shit together themselves, right? But somebody cannot put this together themselves. Like, this is not happening. This is not even happening if you own a large manufacturing company. It's just not happening. Whereas this, I could literally put together in my house. And they saw absolutely no problem to saying, oh yeah, here. I know we spent, 6 figures on R&D to make a really cool device, but here's the schematic that says exactly what every single component is, where it goes, and what it's there for. So it's just part of the culture the culture shift from the time that this thing was created, and now that I just thought it was worth getting across to the people who watch my channel. Anyway, so that being said, let's just go over a little bit of what this does. And I know this is probably overwhelming to a lot of the people who watch my regular laptop repair videos. They probably look at this and they just see a maze. So I'd like to try to do the same thing that I do with the laptop stuff. I'm going to try to break this down into sections to try to explain what each thing does. I'm going to try to remember what each thing does because, to be honest with you, as I look at this, I'm kind of revisiting it for myself because I haven't dealt with, like, this is a linear power supply. I mean, I haven't dealt with the linear power supply in like almost like 7-10 years. This stuff is all foreign to me now. It's just old. And I'm very rusty on it. So let's just try to, I like to look at things from a big picture thinking. So I want you to be able to look at these blocks and kind of understand what they do. But first, I'm just going to go through the individual components. So first thing that's going to happen here is that power is going to come in through the AC outlet. So this is going to be the AC inlet. And that's going to go to this transformer up here. Now the transformer is going to take the higher 120 volts and lower it to something like, I don't know, like 70, 90, 50. I don't know what this amp works off of because it's been forever since I worked on it. And I don't see any numbers here that make that obvious to me. So no clue. It's going to go to the transformer. Now, from the transformer, we're going to have power follow through to, oh boy, these lines are confusing as hell. Let's see, okay, so the lines don't follow through. The transformer over here is labeled T1, right? So let's see, where else in the schematic are we going to find T? This is just a scan. Doesn't have characters. Here we go. T1. Right, over here. So this is T1. So the transformer is going to output to this thing. Now, what the hell is all this shit? Well, this amp is going to have what we call a bipolar power supply. So it has a plus and a minus. So all the time, I'm talking about PP3V3, I'm talking about 3 volts, I'm talking about 5 volts, I'm talking about 12 volts. I'm always giving you positive voltages. But this device, and I'm going to get on to why that is later, uses positive and negative DC voltage. So we have to take the voltage from the wall and turn it into both positive DC and negative DC. And this over here is called a bridge rectifier. So what this does over here, it's a configuration. It's usually a configuration of 4 diodes. Here they have 1 diode in the picture. I don't know if it's because it's a different type of bridge rectifier or if there's really 4 diodes inside that thingy and they just have a picture of 1. But the way a bridge rectifier works is they use diodes in a specific configuration. And the configuration that they use for these diodes is such that it's going to split the AC, the alternating currents, into the pluses and the negatives. So let me just use Microsoft Paint here, so you can see my scribbles. So let's say that AC looks something like this. So if you don't know what AC and DC are, you can watch my AC and DC video. So I'm just going to do a really crappy job of explaining it and drawing it right here. So you have plus alternating. AC is pretty much alternating current, meaning it alternates between positive and negative. So over here, we're going to say 0 volts, and fuck it, I don't care if it's going through. So 0 volts, right, is the line. And you go above the line and you get, let's say, 100 or 150 or 90 or whatever, I don't remember. So it goes up, and then you goes down and you have less voltage. And then you go up and you have positive voltage, and then you go down and you have negative voltage. So what the bridge rectifier is doing is it's taking this, and what it's doing is it's just separating it. So rather than have all this crap and have all this crap, which is positive, negative, the bridge rectifier is going to take the AC and it's going to turn it into DC. So we're going to have separate outputs here. So we're going to have output 1. And output 2 of the bridge rectifier, right? So on output 1, we're going to have something that looks like this. And again, let's just draw this, and we're going to say 0V. So the line represents 0 volts. That's what that's saying. The line represents 0 volts. And just to make that a little less confusing, let's move it into place. So on output 1, you're going to have something that looks like this. Just pretend that those humps are all the same size. And then on output 2, you're going to have something that looks like this. Right? So what the bridge rectifier does is it pretty much separates the hump from the decline. So it separates the positive spikes which are the positive voltage spikes, from the negative voltage spikes. So now output 1 is going to be plus, and output 2 is going to be negative. So going back to the bridge rectifier here, so we have our two outputs, right? So we have this one up here, that's going to be the plus. See where the mouse is moving? You probably can, it's like 1 frame a fucking second. But this is going to be the plus, and down here is going to be the negative. Now what you see in the middle over here is ground, right? So the middle section here is ground, and there are a bunch of capacitors. Now why are there a bunch of capacitors? The capacitors are going to smooth out that voltage. So technically this is not alternating anymore. That's not alternating current because it's only positive. And technically down here, this is not alternating current because it's only negative. But still, come on, it's not alternating, but give me a fucking break. This is bullshit. You're not powering anything properly off of this. This is like an amplifier. This is for all intents and purposes still looks like AC. You need to smooth that out. So what this is going to do, it's going to take all those spikes and it's going to store them so that after the capacitors, you get something that looks like this. Oh yeah, professional production quality here. So you're going to have, so the red line is going to be output, right? So after all the capacitors to ground to smooth it out, you're going to have, let's say, plus 50 volts DC, and down here you'll have minus 50 volts DC. Get it? So that's what the bridge rectifier is doing. So this whole diode thing over here, and if you want to read up on the science of how it does it, you're welcome to. That's not something I'm getting into here. The way this works is it's going to have two outputs. It's going to take the power from the transformer. So the transformer is pretty much going to take the 120 volts of AC and just lower it down because we don't want to work with 120. It's going to lower it to 90 or 70 or 50 or whatever. Once that voltage has been lowered, the bridge rectifier is then going to take the positive end and the negative end and just spit it out separately. And then the capacitors are then going to smooth that voltage out so that once that voltage is then smoothed out, then we can actually use it for the rest of the amp. So this over here is pretty much the power supply. This is the power coming in. So we have a fuse just to make sure that nothing blows if anything's fucked up. We have the bridge rectifier, which is going to be responsible for providing positive and negative. And then we have the capacitors that are going to smooth it so that the power that's outputted is actually usable and not this waving mess. Now up here, I know this looks very, very confusing. What I want you to do is I want you to look at this as separate gain stages, right? So over here, we're going to have, let's say, the input, the tiny. Then over here, we're going to have a slightly larger gain stage. And then over here, we're going to have the big output stage right over here, right? So let me just show you what that looks like on the amp, because if I show you what that looks like on the actual amp itself, it may just help you understand a little better when you can actually visually see the representation. So I'm going to carry the amp over here like an idiot instead of making space on my desk for it like I should, because I'm being a lazy bum at the end of the day. So, and I'm going to turn face focus off on the camera so that you can actually see what I'm talking about. Change the lighting setting here on the camera. All right. So the whole idea here is you're taking the stages and you're going from one to the next to the next. It's not going to take the audio and just take that little 1 volt output, that 1 volt that you have from your MP3 player and turn that into 50 volts for the speaker. It's not going to do that. It's going to do it in little stages. So you have here, let's say you'll have over here, pre-driver, drivers, and then output transistors. So you see how they're all a different size? And you can really clearly tell which ones are the smaller gain stages and which ones are the bigger ones. So the way this works is it's going to take the power, it's going to take it's going to take the music, whatever sound signal that you're sending to it, and it's going to increase it in stages. It's not going to increase it all in one stage. There's separate gain stages going on there. So, back to here. So when you look at all this, I want you to kind of see big picture thinking. So, for example, these are working together. Over here where the mouse is moving in the upper left. These are going to be working together. And then over here, these are going to be working together. Now you may wonder, why is there a mirror image on the other side? Well, the way this works, this is what's called a Class AB amplifier. It's not a Class A amplifier. A Class AB amplifier is an amplifier that's made to be more efficient. The way this is more efficient, and here's what I want you to think about, is before we even get into the efficiency thing, I want to get into how this thing is actually going to create music. A lot of people think that the way this works, what they think is that the amplifier is just taking the voltage and making the smaller voltage into a bigger voltage. They think that there's some magic process by which the transistor takes the tiny voltage and makes it into a bigger voltage. And that's not the case. What's happening here is that the transistor is actually taking a bigger voltage and turning it into a smaller voltage. I know, confusing. So how are we amplifying a signal by taking a big signal and turning it into a little one? Well, the way this works is, remember how I said this is going to be the minus voltage, this is going to be the minus DC voltage down here on this line? Let me just change the capture mode because I'm sick and tired of seeing the mouse look like that. Yeah, we're just going to take off display capture and just do PDF capture. Hopefully this works. Okay, it's working much better. So this over here is going to be the minus voltage down here, and this up here is going to be the plus voltage, right? So let's say that we want to make some music, and here's where I'm going to totally butcher the explanation because I haven't done amplifier repair professionally in like almost 10 years, and even when I did, I wasn't really a theory buff. Let's take up a circuit that you guys are familiar with from my videos. Let's say a no backlight. Let's say a backlight enable circuit. I always talk about the backlight enable voltage, right? I talk about how there's a voltage divider that takes the 12 volts from the backlight circuit and it turns that voltage into 3 volts over here, right? So that's a voltage divider. Now, this is a voltage divider over here, R9731 and R9715. You have one resistor between the high voltage and output and another resistor between here and ground. So the way something like this will work is you're pretty much taking the higher voltage and turning it into a lower one. Now, that's always going to be the same. So if I were to go to something like a voltage divider calculator, so let's do the voltage divider calculator here. So let's say I have 12.6 volts on input, 300,000 ohms for the first resistor, 100,000 ohms for the next resistor. And I do this. I get output 3.15 volts. But let's say what if I were to change this second resistor's value? Well, now the voltage changes. See? So think of this in a similar way. Now, the way I've said a transistor works, and trust me, I understand that a transistor is not a linear device, blah, 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 blah. Well, let's just skip that part because that part's going to confuse the fuck out of a lot of people. So the way, let's say this. Let's say that this is very similar to a resistor. Let me just turn off the screen capture thing again because it's slow as hell. Let's say this is similar to a resistor, right? You have this between here, and then the speaker itself is going to be a path to ground. So let's say that the speaker's own circuitry is going to be where there's going to be a path to ground here. So you have this quote unquote resistor between the high voltage source and here, and then the speaker itself has its own resistance between the plus and the minus terminals. So think of this like a voltage divider that you can vary over time. So this is going to be something like a voltage divider that you can vary over time, that you can vary based on the input. Now, this is not the same as the transistors that you see over here. This is not going to be the same as, where the fuck was I? This is not the same as this. So over here you have transistors that are labeled source, gate, and drain, where voltage is going to flow, drain to source or source to drain, depending on what's on the gate. They're not labeled that way, but this is a different type of transistor, and it follows a lot of the same shit. You can have a base, a collector, and an emitter. Same thing over here. You can have a base, a collector, and a base, collector, and an emitter. I just screwed that up. So base, collector, emitter, right? Very much so, kind of the same shit. Different, different principle on how the insides work and all that, but it's not like for our intents and purposes, it's not crazy different here. So what this is going to do is it's going to allow a certain amount of power to go through to here. Now, what it's going to allow to go through to here is dependent on what's on the base. So what is it that we put on the base? What are we going to put on the base of these transistors so that to adjust the flow of current from here, from the minus and the plus power lines to the output? Music. So we put music on the base. Music is going to be over here. So we have line input. So the music is going to go to the base of the transistor, and that's going to adjust how much of the power from the collector flows through the emitter. So over here, music is going to be on the base, and music is going to decide how much of that 50 volts of DC gets to go to the speaker. Is it going to be, 19 volts now, 20 volts now, 21 volts now? So think of it this way. On one side of that transistor, so let's just do a really shitty print screen here. Do a really shitty print screen. Paste this over here. All right, so here, let's say on the top, we're going to have DC. So let's say at the top of this, on the transistor's collector, we have 50 volts of DC. 50 volts of DC. Now, over here, we have music. So on the base of the transistor, this over here is going to be the base, and I'm going to have music. So this is not DC. This is a waveform. This is musical waveform. I mean, it looks like cock and balls, but it's a musical waveform. Now, what's going to happen here is let's say this is 2 volts, right? This is 2 volts with that awesome handwriting. And this is 50 volts of DC. You're going to put that into the base, and it's going to take this, and it's going to turn it into it's going to take that 50 volts, and it's going to lower the 50 volts, but it's going to lower the 50 volts according, let's make something that makes a little sense here. It's going to lower that 50 volts so that it looks very similar to what was on the base. So let's say I take a nice big brush, and it's going to make it look something like this. Right? So this signal that we have on output, where the hell did my mouse go? That. So this signal that we have on output looks very similar to what we have on input. It's lower than this. So what the transistor has done is it's pretty much taken this very high DC voltage, and it has lowered it but it's lowered it in proportion to the input, right? So this signal over here, this voltage is still going to be higher than this voltage over here. It's a bigger signal. It's a higher voltage, but it can only go as high as the power source of the actual amp. So this can never exceed 50 volts, right? So what this transistor is doing is it's pretty much lowering it's lowering the power supply voltage according to what's on the input. And that's how we get amplification. We actually get amplification by making a bigger signal smaller. It's not by making a smaller signal bigger. And once I understood that, it made understanding the concept of how an amplifier works very simple. And I'm sure I'm doing a shit job of explaining it, but eh. So this over here is my tiny signal. This over here is my bigger signal. But again, my bigger signal over here is still smaller than this. Now, if I ask to keep turning the volume up, eventually I'm going to get to a point where I can't make it any higher because my power supply here on this amp is only 50 volts. So if let's say I make it go all the way up here, what it winds up doing is it just winds up chopping off the top of the signal. So let's say I want to make it as really, really loud. Well, this is what happens. It chops off the top of the signal, and then you wind up with this. And this is what sounds like shit. This is when you get distortion. This is when it sounds like cock and balls. This is how you get clipping. When eventually, at some point, you get so close to the power, the max voltage it can put out. You get to the max voltage that's on your collector, and you can't make the waveform any louder or any more powerful. So this set of transistors over here is going to be doing it for the positive side. Now, down here, you're going to have the same thing happen, but for the negative side. So remember, sound is a waveform. Sound is AC. So let me just delete all this horse shit. So let's just do this again. So let's say that this line over here is going to be 0 volts. So sound is pretty much going to be like this, right? I mean, this is probably really shitty. This is going to sound really poor, but whatever the hell this thing is that I just made, this is kind of AC. It has to have a positive and a negative. Now, what we're doing here to try to make this amplifier a little bit more efficient is rather than having one set of transistors handle both the positive, the pushing, and the negative, the pulling end of it, we're going to have, am I on PDF capture or screen capture? Let's get on PDF capture. We're going to have 2 sets of transistors. One set of transistors is going to do the positive voltage, and the other set of transistors are going to do the negative voltage. You may notice that all these transistors share the same output over here. So this set of transistors the emitter of them is all going to this output, which then goes out over here to my speaker. See this? All these transistors go over here. And then that is going to go to this little relay. And from the relay, it goes to left channel output. So this over here is pretty much the negatives and the positives. And they combine in order to make a full waveform. So the whole way this works is, in an ideal world, you'd be able to make an amp where these are only on during the positive section, and these are only on during the negative section. In reality, if you actually try to make this type of amp with these components be fully Class B, it winds up sounding like shit, because the whole idea is it takes this transistor a little bit of time to wake up when you give it a signal. There's going to be, I think it's something called slew rate. I'm probably getting this all wrong. But it takes this transistor a little bit of time to wake up. And there are a whole bunch of people that say Class A amps sound best because there's no switching. Personally, I don't think most people that say they can tell the difference half a shit from a good Class A/B amp and a Class A amp. So these transistors, in an ideal world, these would only be on for the positive section of the waveform, and these would only be on for the negative section of the waveform. The reality is, it doesn't really work out that well. So the way this works is we have something called biasing, which is going to say, okay, these transistors should be on for this amount of time or for this amount of voltage or whatever. That's a really shitty fucking explanation. These transistors should not be only on for positive. They should be on for a little bit of the negative waveform as well. And these transistors should be on for a little bit of the positive waveform as well. So the whole idea is they're not fully asleep. They're not fully not on. Because if you literally have them switching from a dead state to be on as soon as you give them a signal, you're going to get this really, really crappy sounding output. And this is an amp that you can actually bias into very close to Class A operation. But if you do that, you get more heat, because these will be on even when there's no negative waveform being produced. And again, you don't want these ones being on even when all the time, even when there's no positive waveform being produced. The closer you bias this amp to Class A, the hotter it gets, and the closer you bias it to Class B, the cooler it gets and the less power it uses, but the more it sounds like a piece of shit. So again, you have the stages of the amp here. So you have the beginning of it, the middle, and the end. So each one is kind of boosting the power a little bit on its own before you finally get to output. Let's go over a little bit of the things that most commonly die in these devices, and what some of this other stuff is for here. So you see how there's a resistor between the transistor and the output. So there's this 0.33 ohm resistor over here. The 0.33 ohm resistor sits between the emitter and the output. You see how there's 4 transistors working in parallel? So these 4 transistors are on the positive side. They're all receiving pretty much the same base signal. And there's these transistors over here that are all working in parallel. Well, all of these are going to have slightly different values. What do I mean by that? Well, if I put exactly 2 volts on the base and exactly 50 volts on the collector, every single one of these transistors is going to give me something a tiny bit different on the emitter output. It's just life. You think that this stuff is perfect. It's not. So one of the ways that you mitigate that is by putting this thing called an emitter resistor over here. It just helps make everything a little more stable. You have this 0.33 ohm resistor over here. It's not going. A 0.33 ohm resistor is not going to completely change the sound. It's not going to completely change the amp's ability to deliver power to the speaker. It's almost irrelevant how small the resistance is, but it is relevant in terms of just kind of helping stabilize everything. Now, the other thing that you have to worry about here with these amps is most often, 99% of the time, the way that these amps die is one of these transistors will be shorted. It'll be fucked. It'll be delivering power all the time as much as humanly possibly, fully shorted, and this will destroy everything. So what people will often do is they'll try to find the transistor that's broken and they'll just replace that transistor. Well, remember what I said earlier about how each one of these transistors is going to give a tiny bit of a different value on the emitter for a given value on the collector and the base? Well, that's a tiny difference. But if you were to, let's say, go to a site like Mouser or DigiKey and actually try to buy 50 of these, and just replace that one transistor, it may actually die again. And the reason it's going to die again is because it's going to be uneven loading, because each one of these has to be, they have to be matched in something, I believe it's called beta value. I think it's called beta value. I actually have a machine here, and you're going to laugh when you see how old this fucking thing is, that I used to use to measure this crap before I would replace everything. So this is what I used to use for this. I'm actually a lot older than I say in these videos. I'm 69. and I got this for my 18th birthday. This is a Sencor Transistor Tester, and yeah, in-circuit transistor tester that would tell you the beta value of the fucking transistor. This was, oh man, this is one of those tools that I saved up for such a long time. Look at this thing. Let me just turn the phase focus off so you can see this fucking relic. Hello. Focus. Here we go. I saved up forever to buy this thing. This thing was so cool when I bought it. It saved me so much time. I used to have this jig that I used. I would use a jig to figure out on the table the beta value of the different transistors, and I would match them myself, but that thing saves you so much fucking time. Tools. Anyway, so back to this thing. So if I were to let's say just take 4 transistors of the same model, or 3 of the same model, let's say this 2SA1386 over here. If I were to just take a bunch of these, or 2SC3519s, I've been saying a set of 4 when this is actually a set of 3 this entire time. Yeah, I'm an idiot. Ignore that. When I've been saying that these all work together, these 3 work together, not these 4. I'm being an idiot. Anyway, so let's say I were to take 2 SC3519s that I just bought off of Mouser and put it in there. It's going to fucking blow up again. Because each one of those is going to be, it's not going to be working in parallel. So think of it like, how can I put this? Let's just take an analogy from weightlifting, right? So let's say that in order to properly lift a heavy weight, I need to be doing it evenly. I need to be doing, let's say, this, and then up again. If I'm lifting unevenly because one of my arms or one of my pectoral muscles or whatever is stronger than the other, I'm going to be lifting the bar like this. And if I lift the bar like this, what's going to happen is eventually the weight is going to fall off the bar. So think of it, let's say I didn't put clips on my barbell and I'm doing a flat bench press. If I'm benching like this, I may be able to get the weight all the way up a couple of times, but each time I get the weight up all the way, that plate is going to kind of move further to the end of the bar. And eventually, because I'm benching uneven, the plate on the right side is eventually going to fall all the way off. Now, once that plate on the right falls all the way off, now the left side of the bar is 40 or 50 pounds heavier than the right side of the bar. So now I'm going to get shoved like this, and now that plate is then going to fall off of the bar. So I've hit myself in the chest once. I've hit myself in the chest here. The weight is kind of falling down here. Then it falls down over here. I get hit in the chest. The weights fall off, and I break my bones and everything. It's all very bad. Something very similar happens here. So these are all working in parallel. They're all working together to lift the weight, or in this case, they're working to push and pull the speaker cone. So if they're constantly working and one of these is not lifting as much as the others, or one is lifting more than the others, you're going to get this improportional amplification, which is, long story short, for scientific reasons that I can't get into because I don't know them, is going to destroy those transistors. So a big thing that used to happen is you would have these places that repair general electronics that knew jack shit about hi-fi audio that would say, oh, the transistor is blown. Sure, we'll replace it with a 30-day warranty. And they would replace one, not all of them, they would replace one, and they wouldn't match them. And even worse, sometimes they'd replace all of them, but they wouldn't match the fucking beta value of them. And the shit would blow up again in a month. And then they would replace it again, and it would blow up in a month, and again it would blow up in a month, and they would charge the customer every single time. It's very similar. Every industry has this shit. Now it's with the reflowing dead graphics chips. The person puts the board in an oven, or they reflow the dead graphics chip. They give it back to the customer with a 30-day warranty. The customer comes back on day 31, and the repair shop says, fuck you. This was the very same thing with amps. You had the TV repair shop that was great at fixing TVs, knew jack shit about hi-fi. The TV repair place would replace one of the transistors that was broken. It would come back, another transistor would be blown, and it would just keep going on, and eventually the customer would realize that they were getting scammed, and they'd hate all repair shops. It's one of those things. So that's why if you're going to replace one of those, and you see that there are transistors that are used in parallel in one of these amps, that you should replace all of them, and you should use a device like that, if you can even find it, get into your time machine and go to 1968, buy a Sencor 179 transistor tester, and match all these things. Now let's go over the rest of this. So as I said, a transistor itself is not typically a linear device. So if it's not a linear device, then how do we get sound on output that's the same as the sound that we got on input if we're using transistors every step of the way? One of the things that we use here is something called negative feedback. So, and this is something where I'm probably going to butcher the explanation as well, so engineers, please chime in and and troll me. It's been a long time since I worked on this stuff. So let's say that this is your way. Let's say that this is your music. So I'm just going to go back into Microsoft Paint and try to draw myself some music. So let's say that this here is my music. That's my music. Now let's say I go to amplify it. And it looks like this. So I've made a bigger version of this, but now it has this stupid little fucking spike on it. So what you can do to try to mitigate this is you can send the output after everything's done. You can send that into the input and kind of and make it negative, so that you send back something that doesn't have this little spike in it. Because see, this spike over here that you see was not present in the original. So you can do something like this, where you can send at the output, you can make an arrow back over here, and what you can do is you can send something that looks like this. Nah. Can I even grab that and let's see. Let's do some Microsoft Paint art here. Okay, we take this, and we're gonna flip. Here we go. So now we can send this back into the original audio, and what it's going to do is it's going to then compensate for this bullshit little piece of distortion over here. And again, I've probably butchered the explanation of negative feedback there, so by all means, correct me if I've gotten all of that wrong. But this part over here is going to be the negative feedback. So this AD711 shit and everything around it. So this over here, remember how I said this is going to be output? So this is going to be what goes to my relay, which then goes to my output. The output is going to get fed back over here, and then that is going to follow its way all the way down here until it goes over here, back into the input section. So you're pretty much feeding back the tiny bit of the distortion from the output back into the input, inverted, so that you can then prevent it from happening. Now I know one of the big debates in audio is, wait a second. So if you have to wait until the audio is amplified to get the negative feedback, to feed it back to the input, won't that mean that you've already heard it? Because in order to correct the output has to exist in order for you to send that negative feedback to the input. And you know what? There is a lot of people arguing about that. I know that there's one guy, I think company called IR Acoustics, and he believes that this is important, and he's managed to design a set of high-end amplifiers that has no negative feedback, doesn't use feedback for any of this stuff, that doesn't have distortion. And, again, and there are a couple of other companies that have managed to do the same thing. Some people say I can't hear a difference at all. Some people say it makes a huge difference. My opinion on the matter is that feedback it was only something that you could really obviously hear on those really shitty solid-state amplifiers from the early 70s when they were focusing on maximum power and this dick-waving contest of how much more power can we get over tubes in that era, where you would get things like oscillation and ringing from too much feedback being used. In modern use, I don't really think it's audible, but anyway, I'm sure. So let's just take a look at this now with some big picture thinking, now that we kind of have an idea of what every single piece kind of does. So if we look at this with big picture thinking, I've already explained the transformer. I explained this part? Yeah, okay, explain. All right, so where was I at this? The end. So if we look at this with big picture thinking, we have the power from the AC outlet coming in here. This down here is going to be my power supply. It's going to take my 120 volts of AC, and it's going to take that and lower it to, let's say, 50 volts of AC. This over here is going to split it, so I have 50 volts of AC and 50 volts of DC down here. These capacitors are going to take that and flatten it out. Now that we have my flat power, it's going up here. Here we have the input stage, and here we have, let's say, plus 50 volts of DC and minus 50 volts of DC. And these transistors over here are going to take it and take my little 1 volt line level signal, and this stage is going to take that 50 volts and modulate my 1 volt signal to, let's say, a 5 volt signal. The next stage is going to take that 5 volt signal and then maybe modulate that to, let's say, an 8 or a 10 volt signal. And the next stage is going to take that 50 volts from up here and use that to modulate my 10 volt signal into, let's say, a 30 or a 40 volt signal for the speakers. These emitter resistors are there so that for the final output stage for the one where you really need to be strong. You have three transistors working in parallel on the positive, 3 transistors working in parallel on the negative, and then that over here is then going to go over to a relay. And this relay is going to be hooked up to a protection circuit. So even though you have output, that doesn't actually get to attach to your speakers without going through the relay. And that is that for this amplifier. And now what's happening with my amplifier is that my fuses are blowing on one side. Now there's a short to ground over here and over here. So on my amp, I've got a short to ground both here and here. So this, to me, I'm really hoping it's not a transistor problem. The reason is because I don't want to hunt down a bunch of them and check the beta values. And also, you see how this thing is put together. You saw how this thing was put together before. The transistors are pretty much screwed into a heatsink. That heatsink is then screwed into the whole case. It's a pain in the, and then I have to try to find the compound to reattach them. So that's going to be a pain in the ass. So fixing this is going to be challenging for 2 reasons. A, as if it wasn't evident already, I barely understand how this shit works anymore. And B, where the hell am I going to find the time? But I'm going to try to do a live repair video of this thing. And again, man, you see how many, it's going to be fun. It's going to be fun to try to fix this and make it work again because it does have some sentimental value. It's going to be fun to actually see it work again. And above all, it's going to be fun to see the trolls because you see how many trolls I get when I talk about stuff where I actually know what I'm talking about. So when I'm talking about stuff where I know damn well that if you put me in a room with 100 other people, I'm going to solve the problem faster than them, I'm still getting trolled. So here, I have no idea what I'm talking about anymore. So I can't wait to see all the trolls that show up in the comment section of this video. Hopefully I get some engineer trolls that are actually nice, because I actually would, if I'm getting a lot of this wrong, I would actually like to learn something on how it works. You know, dare I say, maybe I'll even learn how to put this damn thing back together again properly and make it work again. Because I miss having music in my office. I don't have music in my office right now, and it sucks. It's silent in here. I'd rather have silence than a Bluetooth speaker. But I'm going to make this thing work again, because I'm not throwing this thing away. I've fixed this thing so many times. It's had a bad relay. It has had power supply issues. And I actually have had to go through and buy the transistors and match the fucking beta value of them on output and put them all in there. And there's a lot of shit that I've done to this. I intend to keep this thing working as long as humanly possible. So that's it for this video. I'm going to hit stop and head home.